Hi, this is Sung, your online maths mentor, and we're actually towards the end of this particular unit in extension 1. We are doing parametric equations, and we've pretty much done most of it, and most of the questions that you'll see, you should be able to be able to do once you understand basics of parametric equations, because it basically builds on work that you've done in the past with coordinate geometry and with locus and the parabola, functions and relations, etc. Okay, so it should all come together for you. And here is yet another example of a question where we are using our knowledge of parametric equations combined with all the foundational knowledge of everything else to be able to do this question. So let's just launch straight into it and read the question and have a go at doing some of the parts of it. So example 2, 2 points, the first point being P, which is 2AP AP squared, and point Q, 2AQ AQ squared, lie on the parabola x squared equals to 4AY. And we're told that PQ, which is the chord between the two points P and Q, passes through the focus S, right? Let's say the focus is S. Now, on a standard parabola where it's x squared equals to 4AY, where is the focus? Well, the focus is going to be 0A, right? So S is the point 0A. Okay, now we are also told that we need to part 1 of the question, part A, is prove that PQ equals to -1. Now that's often a very common thing that will be asked in this sort of question, right? Where you have a chord that passes through the focus, it's called a focal chord, and usually what that tells us with parametric equations is that PQ equals to -1. I am actually now going to show you how that works, all right? So basically you've got 2 points, you've got P, which is equal to 2AP AP squared, and you've got Q, which is 2AQ AQ squared. Now, how do you work out the equation of PQ? Well, basically you use the 2-point form. Now, the 2-point form from 2-unit maths, you should remember, is equal to y minus y1 is equal to, now m is equal to y2 minus y1 over x2 minus x1, that's your m, x minus x1. Does that make sense? So usually when you have the point gradient form, it's y minus y1 equals to m outside of x minus x1, but m, the formula for m is basically the difference of the y coordinates over the difference over the x coordinates, right? So it's y2 minus y1 over x2 minus x1. And that's basically what we've done. Combine those two formulas together and you get the 2-point form. So here's what we do. Let's make x1 and y1 equal to 2AP AP squared, which means y minus AP squared is equal to x minus 2AP. Now, your m is going to be the difference between y, which can be a outside of p squared minus q squared, over 2a outside of p minus q. Got it? Now, that cancels with that, leaving you with y minus ap squared equals to, now that's the difference of two squares, so you got p plus q times p minus q all over 2 over p minus q x minus 2ap. That cancels with that, which leaves us with y minus ap squared is equal to p plus q onto x minus that times that, which is over 2, which is AP squared minus APQ. That can cancel with that, okay? So you're left with y, which is equal to P plus Q onto x minus APQ, all right? That will be the equation of the focal chord, all right? PQ, focal chord, PQ, the line between P and Q. All right, that's the equation of that. Now, we're also told that it passes through the point 0A, right? So what does that tell you? It means that 0A is going to satisfy this equation, Okay, so if it satisfies this equation, we can put x equals to 0 there, substitute there, and we can put y equals to a there, all right? Because it satisfies that particular, that point satisfies this particular equation, right? Which means that a is going to be equal to, now 0 times all of that, and that's not an a, that's a q by the way. 0 times all of that means that disappears, is equal to minus a p q. Divide both sides by a, and we're left with pq is equal to minus 1. Does that make sense? Which is exactly what we wanted to prove in the first place. Okay, so that's basically the proof of part A, or we've actually solved part A. All right, so now let's have a look at part B. Part B says, show that the point of intersection of tangents at PQ lie on the line y is equal to minus a. Now, what is y is equal to minus a? If the focus is 0a, y is equal to minus a is the directrix, all right, the directrix of the parabola, okay? Which means that the tangents, okay, if this is true, it actually means that the tangents at two particular points on a parabola, if they make a focal chord, their tangents will intersect at the directrix. That's exactly what it means, all right? So let's have a look and see if that's true. Now, tangent at P is equal to, y is equal to px minus ap squared. Tangent at Q is equal to, y is equal to qx minus aq squared. Does that make sense? All right. Now, what we're trying to do from here is work out the point of intersection. Now, the point of intersection will be basically where they're equal to each other, all right? So we can call that equation 1, call that equation 2, and we can solve it, okay? So we've got px minus ap squared, which is equal to qx minus aq squared, all right? And basically what we've done is equated equation 1 and equation 2. So cool. Now all we need to do from here is just solve for x, okay? So let's bring this over to this side. So we're left with px minus qx, and bring this over to this side. So it's ap squared minus aq squared, all right? Now I'm going pretty fast with the algebra here. I am doing that because you are in extension 1 and I expect you, or you should be able to cope with all of this. Having said that, if you need to slow down and be certain for yourself, you know, you can pause as you go and watch things and make sure you're okay with everything line by line, okay? But the beauty of doing it over the internet as a video tutorial is that you can do exactly that. So I'm going to go as hard and as fast as I usually would go and see if you can keep up. So basically what we do from here is p minus q, x equals to a, and this is the difference of t squares, which basically is p minus q, p plus q. That cancels with that, wrong one. That cancels with that, which leaves you with x equaling a outside of p plus q. To find the y coordinate, you then substitute that into any one of those equations. So let's substitute into equation 1, and you should get y is equal to ap, p plus q, minus ap squared. Y is equal to ap squared plus apq minus ap squared. Y is equal to, that cancels with that, which leaves you with apq. Now, what did we say pq is equal to from the last example? Pq is equal to minus 1, right? So we're going to substitute that in, and what we end up with is y is equal to minus 1. Now, that leaves us with the point of intersection. I'll write it as POY. The point of intersection is going to be, now it's not minus 1, it's equal to minus a. The point of intersection is going to be a outside of p plus q and minus a. Now, can you see that minus a is a constant? Minus a is a constant, but all of this is variable, right? The p can change, the q can change, a is a constant. So basically this can take on any value, but the y will always be minus a, which basically tells you that the point of intersection or the locus of the point of intersection of the tangents at P and Q is going to be the line, point of intersection of tangents at P and Q is going to be y is equal to minus a, right? It's going to be equal to y is equal to minus a because x can change, but y will always be minus a, right? So it actually lies on the directrix, which is exactly what we want, okay? And then the last thing that we need to do is show that PQ is equal to all of that. Now, when I say PQ, what I mean is the distance PQ. We're looking for the distance PQ here, okay? So I'm gonna rub this out. I'm gonna leave this up there so that you can actually get a hold of the working out. But I'm gonna rub this out very shortly, and then I will work out the distance PQ and take it from there. Okay, so let's have a look at part C. Now, part C says, show that PQ, right, is equal to A outside of P plus 1 over P in brackets all squared. Now, basically what that means is PQ, the distance PQ, not the equation PQ. Okay, so we're looking for the distance. Now, we will remember that the distance formula is basically x1 plus x2 all squared, so x1 minus x2 all squared, plus y1 minus y2 all squared. Now, does it really matter if it's x1 minus x2 or x2 minus x1? No, it doesn't, okay? We're basically looking for the square of the difference. Now, when we square the difference, anything that's negative will become positive, anything that's positive will also become positive. It comes out in the wash. So in other words, whether we use x2 minus x1 or x1 minus x2, it doesn't matter. The square will take care of it. And again, the square will take care of it here as well, okay? Now, the x coordinates of P and Q are 2AP and 2AQ, right? The y coordinates are going to be AP squared, AQ squared. So what we've got, PQ will be equal to the square root of 2AP minus 2AQ all squared, plus AP squared minus AQ squared all squared, right? What we're going to do from here is we're going to factorize out the A. I'm going to factorize out the A. So basically what we've got is A, but we've got to take note of the fact that when we factorize out the A, we factorize the square out with the A. So it's A squared outside of, and it's 2P minus Q. Do you see that? And I'm going to put that in brackets, all squared, okay? Because what's left over is the 2. But I don't want to factorize the 2 out the front just yet. I want to leave the 2 inside the square, and I want to leave the PQ where it is, okay? And then what I want to do is factorize the A out, okay? And when you factorize the A out, again, it'll be A squared, okay? And in fact, I might use square brackets just to make it clearer what we're doing, okay? And then we're left with P squared minus Q squared, which is the difference of two squares. So I'm going to turn that into a sum by difference. P plus Q, P minus Q, and then in brackets, well, in big brackets, all squared. Okay, now all of this is in square roots, is under a square root sign. So we're going to do that, all right? Okay, what I want you to see is that we can factorize the A squareds out. When we factorize the A squared out of the third, we've got to square root the A squared, which will just be A. What I also want you to see is that there is a PQ that's common and a PQ that's common, both inside a square sign, which when we take them out will be P minus Q all squared, big brackets, 2 squared, plus P plus Q all squared, okay, good. And when we take this P minus Q out, we've got to also square root it. Okay, so when we take it out of the square root sign, we've got to undo the square, or we've got to apply the square root to the square, which means that you've got A outside of P minus Q, and then you've got whatever's left over inside the square root sign. Square that. Square 2 is 4, plus, let's square P plus Q. You're left with P squared plus 2PQ plus Q squared. Got that? All right. Now, here's what I also want you to note. Minus 1 is equal to PQ. We proved that earlier. What I also want you to note is 1 is equal to minus PQ, which is what we're going to do here. So if 1 is equal to minus PQ, 4 lots of 1, or the number 4, is going to be negative 4 lots of PQ. Does that make sense? 4 is going to be negative 4 lots of PQ plus P squared plus 2PQ plus Q squared. Now you can probably see where I'm heading with this, yeah? This minus 4PQ and this plus 2PQ will give a net result of minus 2PQ, which gives us a perfect square. All right, so here's what we end up with. A outside of P minus Q, square root of P squared minus 2PQ plus Q squared. Got it? Which is really nice because what is this the perfect square of? Well, this is the perfect square of P minus Q squared. All right, what's the square root of a square? Well, they kind of cancel each other out. They undo each other. So we're left with A outside of P minus Q times P minus Q, which is A outside of P minus Q all squared. See that? A outside of P minus Q all squared. All right. This is really quite a positive thing because it's starting to look a lot like this. All right. There's a missing piece that we need to kind of put in place to make this complete. Let me show you what it is. All right. Basically, we've got PQ equaling minus 1. What we've got to do is make Q the subject of the formula. Q is equal to minus 1 on P. All right. And we're going to substitute that in to here. So now PQ is equal to A outside of P minus Q all squared, which is going to be equal to A outside of P minus negative 1 on P all squared. Now, these two negatives make a positive, so it's equal to A outside of P plus 1 on P all squared. Bingo, there you have it. This bit is exactly what we're looking for. So PQ is equal to A outside of P plus 1 on P all squared. Okay, so there you have it. So I've given you two examples of parametric type equations. Now there's countless others that could be asked, but as long as you understand that a parametric is treated just like another point, okay, and where the coordinates are an algebraic expression, then you can basically use your coordinate geometry, your geometrical applications of calculus, your algebra, to just work it all out, okay? So in the next episode, I'm just gonna wrap everything all up together and I'm gonna give you a summary of parametric equations, and that will pretty much do the job. So thank you very much for watching. I look forward to seeing you on our last and final episode for this topic. Bye.